do you get killed by?
You? Well, the last dad. Yeah.
Okay.
No, I woke up and I was in the yard eating them. It was a full mood. It was one of those nights.
All right. Okay, Liam. All right. So we are going to start and get as far as we can with this. We should be able to do a lot of it. It's not too extensive. But what we're going to talk about next is implicit differentiation. So a function that is defined explicitly is going to be written like maybe something like this. Y equals x squared plus 3x minus 4. Or it might be something like f of x equals natural log of x plus 2. The key to something being defined explicitly is that you have it solved either for the y or you might call it a f of x. And then everything on this side only has x's. So you only have one variable there. Something that is implicitly defined, to use some that you have seen before, might look like this. X squared plus y squared equals 16. That is an implicitly defined function. That's a circle. What's its radius? 4. And what's the center? 0, 0. Right? Yeah. So that would be an example of an implicitly defined function that you have seen before. It is not solved for it's not solved for a variable with the other variable all on the other side. And in this case, you really can't without making it like a function that has a plus or minus in it. Because if you try to solve that for y, then you would end up with, y squared equals 16 minus x squared, and you have to square root both sides, which means you get a plus or minus there. So you'd really have to break it like into two functions if you did it that way. Something else implicitly defined could be something like, something 3x squared plus 5 cosine y equals xy. You could have x's and y's on both sides. It could be, in general, it's just not solved for a single variable. Some things can be defined explicitly or implicitly. For example, if I've got 2x plus y equals 7. That is defined implicitly. But we could very easily define it explicitly by having y equals negative 2x plus 7, right? Those two are equivalent to each other. One is defined explicitly, the other is implicit. But something like this crazy thing right here can't really be defined explicitly. So far we've looked at only implicitly or explicitly defined functions. So like what we've done so far, we might see a question like find the derivative of y equals 3x squared. Now, we have secretly, in some cases, been doing implicit differentiation without really knowing it at all. Okay? Whenever we take the derivative of this, that y right there, we either call it y prime, or a lot of times I'll call it dy dx equals 6x. Right? Or you could call it a y prime. Either would work. Now, if we take the derivative of y, like pretend like we're just taking the derivative of y with respect to y, what's the derivative of y? 1. It would be 1, right? But we're taking the derivative of this function with respect to x. That's why we have this x right here. We also see, like, over here we got d over dx. That means we're taking the derivative with respect to x. So, on everything we've done so far, we didn't have to really worry about that because everything we were taking the derivative of had an x, right? Or maybe we used a different variable like a t, but we were still taking the derivative with respect to that variable, right? So whenever we take this derivative, we're taking the derivative with respect to x. So like what I'm really doing here is the derivative of y is 1, but because I took the derivative with respect to x, I have to put a dy dx with it. That tells me I took the derivative of y with respect to x. Over here, I took the derivative of 3x squared, which was 6x, and I took the derivative of x with respect to x. But dx over dx is unnecessary to write because that would just be 1. So we haven't been writing that. So whenever we take the derivative with respect to the variable that we're taking the derivative of, we don't have to put anything special with it. We haven't been putting, when we take the derivative of 3x squared, we just do 6x, right? We don't put anything special with it. But if we take the derivative of a different variable, so like for example, this is telling us to take the derivative of this stuff with respect to x. When we take the derivative of a different variable, it's sort of like a chain rule thing. We must multiply it by the derivative of y with respect to x. So like here, I've got 3y squared. I would take the derivative of that, which would be 6y. Just use my whatever derivative rules you would use for that. But because this was a y instead of an x, and I'm taking the derivative with respect to x, I must put with it dy over dx. So let's look at a problem. All right, so one thing, so if we're taking the derivative here of example 1, it is telling us to take the derivative of this expression with respect to x. That bottom is x. It is possible that that bottom could be a y, and that would change things, but it's not really going to happen on the things that we have to see. All right. It's also possible that that could be a totally different variable, like a t. That we will see whenever we get to related rates, but we're not there yet, so you won't see it right now. So if I am taking the derivative with respect of x of 3x plus 2y squared, what I would have is the derivative of 3x is 3. I do not have to put anything with that because I'm taking the derivative of an x with respect to x. So I don't put anything special with that. But over here, I'm taking the derivative of 2y squared. This has a y. So I'm going to get 4y. And because that was a y that I took the derivative of, I must put a dy over dx with it. Okay? For example 2, what type of rule am I going to have to use here? Product. So I'm going to have to use a product rule. So I use the product rule just like I always do. I just have to keep in mind if I take the derivative of anything with a y, I must put a dy dx with it. So I'll have x squared times the derivative of 3y, or y to the third, which is 3y squared dy dx, because I just took the derivative of something with a y. Plus y cubed. Does that need a dy dx? No. It does not, because did I take the derivative? No. So it's just a y cubed times the derivative of x squared, which is 2x. The 2x, when we take that derivative, doesn't need anything because we're taking the derivative of x with respect to x, so it doesn't need anything. Only the y's in this case. So if you clean this up a little bit, it's going to be 3x squared y squared dy dx plus 2xy cubed. You can't, like if there's more than one, you could combine them, and we're going to kind of see that on some of the next problems. So you won't see a lot of problems like this, I don't think. This is kind of just to get us in the mechanics. What we typically see Uh-oh, I didn't mean to do that. What we typically see are explicitly or implicitly defined functions, and they ask us to find a derivative of that. Does anybody know what this is going to be? Oh, wait, no, you don't know what this is going to be. Never mind, you don't know. But you can't use Desmos on your exam, but I like to type these into Desmos just because they are sometimes really cool. And Desmos will graph them. So y to the third plus 2y squared minus y plus 5x squared equals 20. So this makes that kind of weird shape right there. So some of these are really cool. Like if you add plus cosine xy, I didn't do much. What if we do like a e to the xy, kind of like they're kind of fun to like mess around with to get crazy shapes there. They might be circles, they might be ellipses. They are not necessarily functions. Like you can see right here, this is not a function because it does not pass the vertical line test. And that means it can't be written explicitly, like it can't be solved for one variable because it is not a function. It doesn't pass that vertical line test. So I want to find dy dx, which is our derivative, right? The derivative, to find the derivative for implicit differentiation, you're going to take the derivative of both sides with respect to x. Okay, so you will take the derivative of y cubed, which will be 3y squared. What does it need with it? dy dx. Okay, then we will have derivative of 2y squared, which is 4y. Again, a y needs a dy dx. What's the derivative of y? 1. Does that need a dy dx? Luke says yeah. I like if I didn't know anything about this, I could go either way on that. There's no y's left, right? But Luke is correct. You took the derivative of something with a y, so even if the y is not there anymore, you need the dy dx. And then here I've got 5x squared. That's 10x. That does not need dy dx. What's the derivative of 20? 0. So whenever you're looking for dy dx, you want to solve for dy dx. So I think these are pretty cool. The way that you want to go about doing that is you want to move everything with a dy dx to the left side. Technically, I guess it could be the right, but it's usually always going to be on the left. Move everything with a dy dx to the left side. Move all other terms to the right. So on this, I would keep 3y squared dy dx plus 4y dy dx minus 1 dy dx. And then I will move that 10x over to the other side to make it, and I'll make it negative. Now, since everything over here has a dy dx, I can factor out that dy dx. So I got dy dx times 3y squared plus 4y minus 1 equals negative 10x. Okay, then the last thing I need to do is solve for that dy dx. How could I do that here? Dy dx is multiplied by all the stuff in that parentheses. So if I've got multiplication, I want to get rid of it, I divide both sides, right? So I'm going to divide by 3y squared plus 4y minus 1. Here, and those cancel. So I've got dy dx equals negative 10x over 3y squared plus 4y minus 1. This will give us the slope of the tangent line at any point on the graph. But it's different than a lot of the derivatives we had before because you have an x and a y. Right, so if I go over here to this graph just so you guys can see what in the world this means right here. So I'd love to pick a point exactly. Let's pick that point. 2.006 and 2.215. So 2. No, actually that's going to have vertical tangent. Let's see what we got. Let's see. I don't know if I can find the exact point. I guess I can. Let's see if we can. Let's do. No, I can't use that. Let's just do negative. Can I get to negative 1.5 exactly? No. Okay. Negative 1.503, 1.68. Write that down, Luke. Negative 1.503, 1.68. Okay, so if I've got negative 1.503, what did I just say? How have I forgot? 1.68. My brain does not hold enough information. All right, let's label that. We're talking about this point right here. So if I want the slope of the tangent line for that, I would do negative 10 times negative 1.503 divided by 3 times 1.68 squared plus 4 times 1.68 minus 1. There's my slope of my tangent line. So if I want to like draw in the tangent line here, I could do y equals 1.05940566,144. There's my slope. X plus 1.503 plus 1.68, and there's my slope of my tangent line, right? So what this does is it'll find the slope at any point, but you got to plug an x and a y into that equation, right? So that's, now we'll go through how to do that like step by step, all that tangent line stuff. It wasn't asking us for that now, but I could do this at any point on that graph, right? So this right here gives me the slope of the tangent line to this curve at any point, but I have to plug an x and a y coordinate in. I have to have both for that because everything else, we only need the x coordinate. We could do a tangent line just with our x coordinate because our derivative only had x's in it, right? But we'll have to have x and y coordinates for these. So let's look. Again, it is okay to have x's and y's in your answer. In fact, lots of times you do have both in your answer. Let's see. All right, we got time to do this one. What is this one? What's it look like if we graph it? It's a circle, right? So if I take the derivative of this, I'll get 2x plus 2y, but what do I need with that? Y. dy dx. And that will give me 0 over here. Derivative of any whole number is 0. So if I want to solve this one for dy dx, I would need to move my 2x over to the other side. So I've got 2y dy over dx equals negative 2x. And then what's the last thing I would need to do here? Divide by 2y. You don't really factor on this one because there's only one term. And so you would reduce that, and dy over dx would equal negative x over y. Because your 2's would cancel.
Does it happen like pretty much every time on a circle? Doesn't really matter.
I've got example 5 there for a reason. I think it's going to be similar, but I can't remember exactly right off the top of my head right here. Definitely, Luke, it would not matter what your radius was. Your radius could be 100, it could be 49, it could be square root of 3. Couldn't be infinity, because then it wouldn't really exist. But it could be all the way up to infinity. It could be any number right there, and you would still get the same derivative no matter what. Now, 5 is still a circle, but the center is not at 0, 0, so I think we're going to see something different out of it. All right, so